Hello learners, on behalf of Indira Gandhi National Open University, myself Subhasis Maji, Professor in Mechanical Engineering of School of Engineering and Technology, discussing today's topic, that is applications on energy and energy transfer. This is the third module of the course Thermodynamics and its application. In our earlier two lectures, we introduced the course, that is Thermodynamics. We discussed some important properties like pressure, volume, temperature, specific heat, and also in the second module we discussed energy and energy transfer. So today we are going to discuss applications on energy and energy transfer. Let us discuss about the objectives of today's discussion. After listening in this video lecture, you will be able to define and understand energy from a thermodynamic viewpoint. You will be able to know different types of energy transfer. You will be able to understand how thermodynamics is useful in different disciplines of engineering, and you will also be able to solve problems related to energy transfer. Before discussing the main topic, let us first discuss the matching problem. So there are two columns, column A and column B. In column A, 4 items are given: a mug of coffee, second item is given as a piece of coal, and third item is given as a coiled spring, and the fourth item is a moving bicycle. And in column B, the 4 types of energies are given: A, kinetic energy, B, elastic energy, C, chemical energy, and D, heat energy. Now we have to see which is matching what. A mug of coffee, definitely when you think of hot coffee, it is related to heat energy. A piece of coal, you all know that coal is a conventional fuel and chemical energy is stored in a coal. So a piece of coal will be matching with chemical energy. A coiled spring, now when the spring is compressed, a potential energy, we call it the elastic energy stored within the coil, and the elastic energy stored within the coil is expressed as half kx square, where k is the spring constant and x is the compression of the spring. So a coiled spring is matching with elastic energy, and the fourth one is a moving bicycle, and since it is having a velocity, so it is related to kinetic energy. So a mug of coffee is matching with heat energy, a piece of coal matching with chemical energy, a coiled spring is matching with elastic energy, and a moving bicycle is matching with kinetic energy. Now let us discuss about the energy transfer. Energy can be changed from one form to another. Example, a candle contains chemical energy. When the candle burns, the chemical energy is transformed into heat energy plus light energy. Electric energy can be transformed into light energy, sound energy, heat energy. Here you are seeing 2 pictures. One is television and another one is radio. When you switch on the television, then you are using electrical energy, and when the television is on, you can see the picture, you can feel the sound, and also you can see the light, and also you will find some heat is being also generated. So electrical energy is converted into light energy, sound energy and heat energy. Same thing is for radio also. Now you see in the picture there is a storage battery. So we can trace how energy is transformed when we look at some everyday situation. You might have seen the storage battery. This has been used in the car. Now the chemical energy transform into heat energy and electrical energy. This is the example for a battery. When the battery is used in a car, we can switch on the light, or because current is flowing through the circuit, that means chemical energy is transformed into electrical energy and heat energy because heat is also generated. Kinetic energy transform into sound energy, heat energy and electrical energy. This picture is shown some wind turbine, and wind turbine is for generating electricity, and when the wind turbine is on, there is heat energy as well as some sound energy also evolved. So this is a very good examples for kinetic energy is transformed into electrical energy, heat energy and sound energy with the examples of windmill. And windmills are there so that we can make use of the kinetic energy associated with the moving air, and we can transform into electricity, and in turn the kinetic energy will be converting into sound energy, heat energy and electrical energy. Let us discuss in a control volume. The control volume is also known as open system. Now here you see we have considered a control volume, and m dot in is the rate of mass entering into the control volume, and m dot out is the rate of mass leaving from the control volume. Let us see what expressions we get for the rate of accumulation of mass. The rate of accumulation of mass within the control volume is defined as dou mCV by dou T. So dou mCV by dou T is the rate of mass accumulated within the control volume is equal to m dot in minus m dot out. But when you think of a steady state, we know that in a steady state the properties will not change with time. So in a steady state, dou mCV by dou T is equal to 0. So finally we are getting the expression for the steady state, that m dot in is equal to m dot out. That means the rate of mass entering into the control volume is equal to the rate of mass going out from the control volume. For the same control volume, which is also called open system, we are discussing about the conservation of energy. Here you see that E dot in is the rate of energy entering into the control volume, E dot out is the rate of energy leaving out from the control volume, and here Q dot CV is the rate of heat entering into the control volume, and W dot is the rate of work done leaving out from the control volume. So if you write the E dot net, that is the net energy in the control volume entering, is E dot in minus E dot out. So E dot net is equal to E dot in minus E dot out, and Q dot CV is the rate of heat entering into the control volume, and W dot is the rate of work done by the control volume. So the rate of change of energy within the control volume, that is dou ECV by dou T is equal to E dot net plus Q dot CV plus W dot. Now this expression is given for the change in energy, the rate of change of energy within the control volume. Now for a steady state, we all know that property will not change with time. So for a steady state, dou ECV by dou T is equal to 0. So for a steady state, the equation is equal to E dot net plus Q dot CV plus W dot is equal to 0. Now this picture is for thermal power plant. In thermal power plant, in the last class we had discussed that there are 4 important components. One is boiler, second one is turbine, third one is condenser, and the fourth one is pump. Now we will see that how the energy transfer is going on in each and every component. When you think of a boiler, so purpose of the boiler is for converting water into high pressure, high temperature steam. How it is possible? See, when the coal is burned, the chemical energy is converted into heat energy. So in the boiler, there is a transformation of energy from chemical energy, which is within the coal. When it is burned, it is converting into heat energy. And see that high pressure, high temperature steam is entering into the turbine. Now what is going on in the turbine? That high pressure, high temperature, when it is entering into the turbine, the shaft of the turbine rotates and the shaft of the generator is coupled with the shaft of the turbine. That means the kinetic energy due to the rotation of the shaft of the turbine is converting into energy, because energy is produced by the generator. And the low pressure, low temperature steam is entering into the condenser. It is condensed into water, and the purpose of the pump is for pumping the water into the boiler. It is a cyclic process. Now this is a diagram for the steam power plant. You see there is a boiler, and where coal is burnt, the steam is generated. That steam, high pressure, high temperature steam, is entering into the turbine. The turbine shaft rotates, and the shaft of the turbine is coupled with the shaft of the generator, which is producing electricity. So in the boiler, that chemical energy is transformed into heat energy, and in the turbine, the heat energy is converting into kinetic energy due to radiation, and the generator, it is the kinetic energy is transformed into electricity. So this is the diagram, and in our later classes we will discuss much about the thermal power plant. Now let us discuss some numericals. So far we have discussed how to calculate work done for constant pressure process, for isothermal process, for polytropic process, but now we will see how we can solve the problems for different cases. Here you see that one diagram is given. The process occurs from A to C, but let us first read the problems, what problem is telling. Find the total work done in megajoules by a gas system going from state A to state C along the path as shown in the figure. You see from A to B, it is a constant pressure process. The pressure is given as 60 bar. So, and the initial volume A is given, that is 0.2 meter cube, and the final point at point B, the volume is also given. So initial pressure is given as 60 bar, and at point A the initial volume is given as 0.2 meter cube, and at point B the final volume is also given, that is 0.5 meter cube. So we can calculate the work done. That expression for the work done for constant pressure process is known. Now from B to C, that at the point B volume is given 0.5 meter cube, and at point C the volume is also given, but the pressure at C is not given. Now let us see how we can calculate the pressure at point C. If you want to calculate the pressure at point C, we can use the polytropic equations, that is PV VV to the power n is equal to PC VC to the power n. Now you see PV is 60 bar, VV is given as 0.5 meter cube, BC is given as 1 meter cube, only PC is unknown, so PC we can calculate, that comes out to be 24.36 bar. Now for net work done, initially it is a constant pressure process. Expression is PB within bracket VB minus VA plus the isothermal process, that is P, that expression is also known. But from B to C, it is a polytropic process. So polytropic process, the work done is given as PVVB minus PCVC whole divided by N minus 1. So you know pressure at point B, you know pressure at point C, you know the volume at point A, volume at point B and volume at point C, and you know the value of N, that is 1.3. So you put the value in that expression for the work done, and finally you can calculate the net work done for this process, and this result is coming out as positive because it is an expansion process, that is work done by the system. Let us discuss the second problem. If a gas of volume 7500 centimeter cube and at a pressure of 100 kilopascal is compressed quasi-statically according to PV square is equal to constant until the volume becomes 2500 centimeter cube. Determine the final pressure and the work done. See, from this polytropic equations, P1 V1 to the power square is equal to P2 V2 square. So we can calculate the final pressure, that is P2 is equal to P1 within bracket V1 by V2 whole square. So P1 is given as 100 kilopascal and V1 is given, that is 7500, V2 is given as 2500 centimeter cube. So P2 we can calculate, that is 900 kilopascal, and the work done for a polytropic process we know that is equal to P1 V1 minus P2 V2 whole divided by N minus 1. So here P1 is given as 100 kilopascal, V1 is 7500 centimeter cube, P2 we have calculated 900 kilopascal and V2 is 2500 centimeter cube. The value of N is given 2. So if you substitute all these values, you can get the final work done, that is minus 1.5 kilojoule. Here you are getting minus because it is work done onto the system. That's why it is coming negative as per the sign convention. Because we know very well that work done by the system is positive and work done onto the system is negative. Now let us discuss the third example. It is a very interesting problem. The flow energy of 0.18 meter cube per minute of a fluid crossing a boundary of a system is 25 kilowatt. Find the pressure at this point. Now we know very well that pressure is equal to force per area, but here power is given, but we know that power is equal to force into velocity. So you divide F by A and multiply A with V. That means we are multiplying numerator and denominator both by A. So F by A, that is force per area, comes out to be pressure, and V into A, that is velocity and area, will be equivalent to volumetric flow rate. So from this expression you can calculate pressure is equal to power divided by volumetric flow rate. Power is given as 25 kilowatt and volumetric flow rate is given as 0.18 meter cube per minute. We have to convert it into meter cube per second. So 0.8 divided by 60 will become meter cube per second, and if you put all these values of power and volumetric flow rate, you will get the pressure. So the pressure will come out to be 8333.33 kilopascal. Now let us see the example 4. It says that a milk chilling unit can remove heat from the milk at the rate of 48.92 megajoule per hour. Heat leaks into the milk from the surrounding at an average of 5.12 megajoule per hour. Find the time required for cooling a batch of 600 kg of milk from 50 degrees centigrade to 5 degrees centigrade. The specific heated concentration of milk is given as 4.187 kilojoule per kg. First of all, let us see that what is the net effective heat removal rate. Now, the net rate of cooling is 48.92 minus 5.12, that is equal to 43.80 megajoule per hour equal to 43.80 into 10 to the power 3 kilojoule per hour, because 1 megajoule is equal to 10 to the power 3 kilojoule. So here the net heat to be removed equal to 600 into 45 into 4.187 kilojoule, because we know very well that Q is equal to ms delta T. So M is mass is given 600 kg and S, that is the specific heat at constant pressure, is given as 4.18, and the temperature difference delta T is 50 minus 5, it is 45. So time required is equal to net heat to be removed divided by net rate of cooling. So that is that if you put both the values, the final result will come out to be 2.58 hour, that is equal to 2 hours 35 minutes. Now the next problem is also very interesting, that is 950 kg of fish at 10 degrees centigrade are to be frozen and stored at minus 10 degrees centigrade. The specific heat of fish above freezing point is 3.312, below freezing point is 1.662 kilojoule per kg. The freezing point is minus 2 degrees centigrade and the latent heat of fusion is 229.85 kilojoule per kg. How much heat must be removed to cool the fish and what percent of this is latent heat? This is very interesting because we are cooling the fish from temperature 10 degrees centigrade to minus 10 degrees centigrade, but the freezing point for the fish is minus 2 degrees centigrade. So first of all, we have to cool down the fish from 10 degrees centigrade to minus 10 degrees centigrade at 3 stages. From cooling from 10 degrees centigrade to minus 2 degrees centigrade and minus 2 degrees centigrade, we have to remove the latent heat so that it will be completely freeze. After that, we have to reduce the temperature from minus 2 degrees centigrade to minus 10 degrees centigrade. Now let us see how we can do this problem. First stage, cooling of fish from 10 degrees centigrade to minus 2 degrees centigrade. Second stage, removing of latent heat at minus 2 degrees centigrade. And third stage is cooling of fish from minus 2 degrees centigrade to minus 10 degrees centigrade. Net heat to be removed to cool the fish from 10 degrees centigrade to minus 10 degrees centigrade is 950 into 3.312 multiplied within bracket 10 minus of minus 2. That heat is removed from cooling the fish from 10 degrees centigrade to minus 2 degrees centigrade, and then the next term, that is plus 950 into 229.85, that is to remove the latent heat so that it will be completely freeze. And the third part of the cooling is for cooling the fish from minus 2 degrees centigrade to minus 10 degrees centigrade. If you calculate, the final result will be 268.75 megajoule. But out of 3 cooling part, so the second part is for the cooling of latent heat. So the percentage of latent heat will be 950 into 229 divided by total heat of cooling, that is 268,745.5 kilojoule, and that comes out to be 81.25%. Next problem. An electric generator coupled to windmill produces an average electric power output of 7.5 kilowatt. The power is used to charge a storage battery. Heat transfer from the battery to the surrounding occurs at a constant rate of 0.75 kilowatt. Determine the total amount of energy stored in the battery in kilojoule in 10 hours of operation. So you see that the net rate of charge is equal to 7.5 minus 0.75, that is 6.75 kilowatt, and the total amount of energy stored in the battery is 6.75 into 10 into 3600. Why we are multiplying 3600? Because we have to convert 10 hours into second. That's why we have multiplied 3600, and the final result will come out to be 2.43 into 10 to the power 5 kilojoule. Now the example 7, the gas within a cylinder piston arrangement undergoes an expansion process with the gas pressure given by a polytropic process, that is PV to the power n is constant. The initial pressure is 0.35 megapascal. The initial volume is given as 0.15 meter cube, and the final volume is given as 0.30 meter cube. Determine the work done for the process in kilojoule. Here for the three cases we have to do it when you think of n is equal to 1.5. It is a polytropic process. So for the polytropic process we must know the final pressure, that is P2. So how to calculate the P2? That we have already discussed, that P1 V1 to the power 1.5 is equal to P2 V2 to the power 1.25. So P1 is known, V1, V2 are known. So we can calculate P2, that is equal to 0.124 megapascal. Now you see the net work done for the polytropic process, that is P1 V1 minus P2 V2 whole divided by n minus 1. P1 P2 V1 V2 and n all are known. Just put the value in the expression for the work done and get the final result as 30.6 kilojoule. For B, n is equal to 1. When you put in the polytropic process n is equal to 1, that is nothing but PV is equal to constant, that is isothermal process. For isothermal process we know the expression for the net work done, that is P1 V1 log V2 by V1, and if you put all these values you will get the final result for work done, that comes out to be 36.39 kilojoule. For the third part, when n is equal to 0, PV to the power n is equal to 0 is equal to constant. If you put n is equal to 0, that means P is constant. This is nothing but constant pressure process. For the constant pressure process, we know the net work done is equal to P1 within bracket V2 minus V1. V1 is known, V2 is known, P1 is known. So you put the values of P1, V1 and V2 and get the answers for net work done, that comes out to be 52.5 kilojoule. Now for the next problem, that is example 8. The drag force Fd imposed by the surrounding air on an automobile moving with a velocity v is given by Fd equal to CD A half rho v square. Here CD is the drag coefficient, A is the area, projected area, rho is the density of the fluid, and v is the velocity of the fluid. In this case CD is given as 0.45, area is given 2.25 meter square, rho is given as 1.22 kg per meter cube. Calculate the power required in kilowatt to overcome the drag at a constant velocity of 120 km per hour. See, first of all we have to calculate Fd, that is the drag force. Once you calculate Fd, then there is no problem for calculating power, because power is known as force into velocity. Now let us see how we can do this problem. See, velocity is given 120 km per hour. We have to convert into meter per second. So 120 into 1000 divided by 3600. So velocity is equal to 33.33 meter per second. And the drag force expression for F is given, Fd is given as CD A half rho v square. Put all the values given, calculate the magnitude of the drag force, that comes out to be 686.25 Newton, and the power is force into velocity. Force is drag force, you have already calculated 86.25 Newton, and velocity is given 33.33 meter per second. Just multiply it and final result you will get 22872.71 watt. But if you want to convert kilowatt, you have to divide by 1000 and the final result will be 22.87 kilowatt. Now you see how we can calculate different problems with energy and energy transformations. So in this case, initially we have discussed about different forms of energy, how the energy conversions takes place with different examples. We have discussed about the control volume, and control volume is also known as control mass. We have seen how to get the expressions for the mass flow rate, and we have also discussed the mass flow rate for a control volume. For a steady state condition is nothing but m dot in is equal to m dot out. M dot in is the rate of mass entering into the control volume, and m dot out is the rate of mass leaving out from the control volume. We have also discussed several numericals so that we can tackle any problems related to energy and energy transfer. Now let us summarize what we have discussed in today's lecture session. We have discussed several points like energy from a thermodynamic viewpoint, different types of energy transfer, mass transfer through a control volume, energy transfer through a control volume, energy transfer with an example of steam power plant, and we had seen that how the energy transfer takes place at different components of a steam power plant. In a boiler, the chemical energy is transformed into heat energy. In turbine, the heat energy is transformed into kinetic energy due to rotation, and in the generator, the kinetic energy due to rotation is transformed into electrical energy. And we have solved some beautiful problems related to energy transfers. So today we are winding up over here for this class, and next class we will discuss about the properties of pure substances in the next module. Thank you very much.